Okay, today we're going to be looking more in depth at this type of energy called thermal energy, which you guys already learned about last time. So by now you should be masters of the idea of energy conservation, which will be coming up time and time again. You should be masters of mechanical energy, and hopefully you remember that mechanical energy involves large objects, like I think there was a problem involved a ball falling off a cliff, or a rocket being launched from the ground. So those large objects involve mechanical energy. We talked mainly about gravitational potential, kinetic, how energy can flow back and forth between those. We're going to end up today talking about other types of kinetic energy, energy dealing with motion, and other types of potential energy, energy dealing with the arrangement of particles in a system. Remember that this ball on top of a cliff has potential energy simply because of how it is arranged, how the system is arranged. The Earth is down here, the ball is elevated up here. The arrangement of particles in the system gives it its high amounts of potential energy. So kinetic energy, energy of motion, potential energy, energy dealing with arrangements. It's going to come back today, but in a different way. Now, instead of looking at these large substances, these large objects, and talking about mechanical energy, we're going to be talking about thermal energy, which I hope you remember is defined as the energy due to the random motion of tiny particles. So we're looking at atoms, we're looking at molecules, all right? This entire lecture today is going to be based on this theory, this idea. So this is very important to get down. It's called the kinetic molecular theory. And I think this name will make lots of good sense when you see the definition. This is the idea that all matter is composed of tiny particles. There's the molecular part. In random constant motion. There's the kinetic part. Kinetic molecular theory. Tiny particles in random constant motion. And you know this already too, that this motion corresponds somehow to heat and temperature, heat being just another word for thermal energy. So we're going to analyze these two in more detail right now and get some definitions. So here's an expanded definition of thermal energy. I think last time you saw that thermal energy is just the energy of that random motion. Particles are in constant random motion. We could take some time and I could prove this to you. You guys have all experienced this. If you have a cup of water and you drop some food dye into the water, um, what's going to happen to the food dye? Is it going to stay in one spot? No, all on its own is going to start to disperse and start to slowly spread out in your cup of water. Why is that happening? Because it's made of particles, and those particles are moving. They're vibrating. They're constantly flowing over each other, constant random motion. You can see it very simply just with a cup of water and some food coloring. So particles are in constant random motion. They're moving, which means they have energy. They have kinetic energy, right? So this is actually a type of kinetic energy on the molecular level, on the scale of tiny particles. The important thing to keep in mind is that when we use the term thermal energy or heat, we are talking about the total amount of energy of some collection of particles. So let's imagine that we have a cup of water or something, and it's composed of water molecules, which I'm going to represent just simply with these dots. And those water molecules are moving. If I was to measure the kinetic energy of all of those water molecules, notice I'm making them move in random directions. If I was to add up all the kinetic energy of those particles, I would get the total kinetic energy of all those particles moving, and that would be the thermal energy. It's the total amount of random motion, the total kinetic energy of a collection of particles in a substance. Because it is the total, it depends on two things: how quickly the particles are moving and how many particles there are. So let's imagine this. Let's say that I have a smaller sample of water, and the particles are moving just as fast. Which one has more thermal energy? Well, this one does, obviously, because there's more stuff there. So it depends on how many particles there are, and it depends on how quickly they're moving. So let's look at this. This diagram is actually a little bit more complicated than what I'm talking about, but we'll analyze it more in depth later. Let's say that these two substances, they have the same number of particles, 1, 2, 3, 4, 1, 2, 3, 4. Of course, this is an oversimplification. There would be billions and billions. So they have the same amount of particles. So how many particles there are, that's the same. But these guys on the left, substance A, you can see these particles are moving much more quickly. They have more motion, more kinetic energy. So we would say that substance A contains more thermal energy. You'll notice that it also has a higher temperature. But don't get this confused. Temperature is actually a different concept. Temperature is a measurement of the average kinetic energy of particles in a sample, of particles in the substance. We're not looking at total anymore. The keyword here is average. Let's say that you have a mug of hot coffee or something. I'm a professional artist, by the way. That's why my drawings are always so great. Those particles, because it's very, very hot, they're moving very rapidly. So I'm going to draw very large velocity vectors here. So there's my cup of coffee. And let's say over here I have this big bathtub. And it is full of just warm water. So I have lots of particles, but they are moving much more slowly. If I asked you which one had the highest temperature, I think you'd pretty easily be able to tell me that this one has a higher temperature. It's hot. It's hot coffee. The particles are moving very quickly. This one has a lower temperature. What if I asked you which one has a higher thermal energy content? The answer would actually be this one. Why? Just because it has immensely more particles. Remember, thermal energy is all about the total. I'm going to refer to thermal energy as ETH. So thermal energy deals with the speed of the particles, or the velocity, and the number of particles, how many particles you have. So even though these are moving more slowly, I have more of them. And so technically speaking, this would have a higher thermal energy content. So thermal energy deals with the overall number of particles and how quickly they're moving. Temperature is just an average. The average particle here is moving much more slowly than the average individual particle in my cup of hot coffee. So temperature is an average kinetic energy. Thermal is a total. I hope that helps you see the difference. We measure temperature in two different units, scientifically speaking. The Celsius scale. This is a scale that is based on the freezing points and boiling points of water. So hopefully you guys know that water will freeze at 0 degrees Celsius and will boil at 100 degrees Celsius. That's how this scale is defined. It was defined as, okay, water freezes at 0, water boils at 100, make 100 increments in between, and there's your temperature scale. So that's pretty simple. The Kelvin scale is one you may not have heard about. It was invented by a guy named Lord Kelvin in the 17 or 1800s. He studied things like thermal energy and stuff like this. This is different because it's an absolute scale. It has no reference point. For example, Celsius has its reference point as the freezing point and boiling point of water. We would not be able to define Celsius without that reference, without looking at water as our reference substance. Kelvin is absolute, which means that 0 is the lowest you can go. 0 Kelvin means 0 kinetic energy. We call that absolute 0. At absolute 0, the particles stop moving. They have no motion at all. You cannot get colder than absolute 0. You can get colder than the freezing point of water. It happens often in some places in the wintertime. But we cannot get colder than absolute 0, 0 Kelvin. Absolutely no random motion, absolute 0. It's an absolute scale. Here is how you convert between Celsius and Kelvin. All you have to do to calculate the Kelvin temperature is take the Celsius temperature and add 273. So the freezing point of water in Kelvin would very simply be, the freezing point of water in degrees Celsius is 0. Slap a 273 on that, we're going to get that the Kelvin temperature is 273. Water freezes at 273 Kelvin. It is not degrees Kelvin. We don't say degrees Kelvin because it's not based on reference points. It's an absolute scale. So 273 Kelvin would be the freezing point of water. What would the boiling point be? Well, to find the boiling point, we take the Celsius boiling point of water, which is 100, and we once again add 273. Very simple. 373 Kelvin would be the boiling point of water in the Kelvin scale. Simple enough. So temperature is an average kinetic energy. Thermal is the total. And once again, we're talking about the motion, the random motion of tiny particles in a substance. Another important distinction between temperature and thermal energy is that thermal energy is a type of energy, so it can be transferred between objects. It can flow. We talk about heat flowing from one substance to another. There's a very simple rule that we follow to figure out how energy flows in this manner. Thermal energy is always transferred from high temperature to low temperature, so from objects with higher temp to objects with lower temp. And that transfer will occur until both objects reach the exact same temperature, when we refer to that as thermal equilibrium. No more energy can get passed back and forth overall when this has been reached. So let's look back here at our example of substance A and B. Substance A has higher thermal energy, higher motion on average, so a higher temperature. Substance B has lower motion on average, lower temperature. If we bring these two substances in contact with each other, something's going to start happening. Heat is going to flow. Heat energy will flow. And you can see it's going to flow from substance A into substance B. Why? Because it always flows from high temperature to low temperature. Substance A is our higher temperature object. So the heat energy will flow from substance A into substance B. Eventually what happens is that the particles will reach the same average speed, the same average kinetic energy, the same temperature, and thus they are unable to pass total energy back and forth. And we say that they have reached, that the system, this whole system has reached thermal equilibrium. Now, why exactly is this happening? What exactly is happening with the particles to transfer this energy? Great question. I'm glad you asked. It's all about the motion of the particles, the fact that the particles are moving and that they are colliding with each other. So think about this. If we bring those two blocks in contact with each other, a hot particle from one is going to collide with a cooler particle from the other substance. So here you can see my cold particle has low motion, my hot particle has high amounts of thermal motion, high amounts of kinetic energy. And they're going to collide. What happens during a collision? Well, some energy is going to get passed, some energy is going to get transferred from the fast object into the slow object. And so this object is going to increase its energy, which you can see here. It's moving more quickly. This object is going to decrease its energy. It's going to start moving more slowly. Have we destroyed energy? No, the total energy content is the same. It's just been transferred. And so we end up with two particles that we now can maybe say are in between or warm. They have the same amount of energy. So if we think about this as particles colliding, this makes perfect sense, what I've said earlier, that energy will flow from high temperature to low temperature. When you bring these two substances in contact with each other, the particles are going to start colliding. Substance A has particles that are moving more quickly. They're going to collide with the particles of substance B, transfer their energy, transfer their kinetic energy. It's just kinetic energy on a small scale. When they transfer their kinetic energy through collision, a particle in substance B will speed up a little bit, and a particle in substance A that gave away its energy is going to slow down a little bit. And this is going to keep happening until eventually they all have the same velocity, the same average speed, the same average kinetic energy. And so collisions are going to result in no transfer, no net overall transfer of kinetic energy. So once again, we have to think about it in terms of collisions transferring kinetic energy. Here's another picture of that. You can see this is exactly what's happening back here on this slide when my hot substance is touching my cold substance. The high temperature substance, this particle is moving very rapidly because this substance has a high temperature. My low temperature substance, this particle is moving very slowly. These particles are on a collision course. They're going to collide with each other, bounce off of each other, and you can see what has happened. This substance with a large velocity, large kinetic energy, has transferred some of that kinetic energy to this low energy particle. So this one ends up with less kinetic energy. This one ends up with more kinetic energy. This keeps happening, and overall we can say that heat energy has gone from the high temperature object to the low temperature object, just like so.